Hello and welcome back. We just spent a couple of videos talking about edges and how important it is to compute edges in order to obtain image segmentation. In this video, we're going to present Otsu's method. Otsu basically looks at the histogram of the image. It looks at the pixel values and looks at the property that in order to obtain segments, we need kind of uniform pixel values. So it's not looking at edges, it's looking at the regions inside the segments that we want to segment out, the objects that we want to segment out. Let's look at the basic underlying idea behind Otsu, what motivates this algorithm, and then we're going to explain how it works. If we look at this image of a fingerprint, we plot the histogram, and the histogram is what's called bimodal. A lot of pixels values are here, which is basically a lot of the fingerprint, and a lot of pixel values are here, which is basically the background. Very clear two modes in the histogram. So this is a multimodal histogram. And the basic idea is that if we threshold here, we can obtain a very simple segmentation. We just separate the fingerprint marks from the background by a simple threshold because we have this bimodal distribution. Otsu is going to help us to find basically the threshold in an automatic fashion. Now, of course, not all the time images are as nicely distributed as this one. Let us look at this very simple example. Here we have a binary image. So we have still bimodal distribution, but just two delta functions. If we add a little bit of noise, then we're going to still get, so this is Gaussian noise, we're still going to get two modalities. And Otsu is going to be able to, without any problem, Otsu's method is going to be able to segment this out with no problem. It's going to find the threshold. Now, if we add much more noise, the variance is about 5 times going from here to here. Now the histogram is much more distributed. We don't have this multimodality, and Otsu's method is not gonna be able to find a nice threshold. I haven't explained to you the method yet, but if we apply the method to this image, because of this distribution, this is what we're gonna get. We're not gonna be able to segment it out. But of course, at this time, 5th week in image processing, we're not really scared of noise. We see a noisy image, we can denoise it. If we denoise, we might be able to get back, in this case, we get back to this bimodal distribution, and then Otsu's automatic threshold algorithm is going to be able to segment it back. So it's a very powerful technique, as we're going to see. This is a simple image to illustrate the idea. So what is the method trying to do? The method is trying to find a threshold such that the in-class variability is very small. So we want to find a threshold here such that the variance on each one of the classes is as small as possible, so the class is as compact as possible. And the method starts from the histogram. There is no spatial relationship here. So we lost the spatial relationship. So regions that have similar pixel values but are in completely different positions in the image will kind of be merged in the histogram, and then Otsu's algorithm is going to treat them as the same. So we're going to see later on other algorithms that take into account the spatial relationship between the pixels, but this doesn't. The basic idea is very simple. We need to minimize the weighted within class variance. We assume 2 classes, and we need to minimize the weighted within class variance. So what's that class variance? Is defined here. T is going to be the threshold. That's the threshold we are looking for. It's going to be, if we have a regular image, it's going to be some value between 0 and 255. And this is the value we're trying to minimize for. And let me define each one of these variables here, although they're pretty clear. So this is basically the probability of each one of the classes. P is what we get from the histogram. We start from the histogram, we have a probability for every pixel value. So we compute the histogram and we normalize it, so it's a probability, as we have taught a few weeks before. And then we go from 1 to t, that's where we put the threshold, or from t plus 1 to the end of the largest pixel value, 255, and then we get the probability for class 1, the probability for class 2. Then we simply get the means for class 1 and for class 2, and then we also get the variance for class 1 and the variance for class 2, and in such a way we obtain the weighted within class variance, which is here. And that's what we want to minimize. Once again, this measurement basically gives us the compactness of the classes. If we put the threshold in the wrong place, there's going to be large variance for one of the classes, and we don't want that. So that's what we need to optimize. That's what Otsu's algorithm does. Now, how to implement this? One way is extremely trivial. You just try it. You go for t equals 0, you compute this, not hard, and then you compute this value. You do the same for 1, 2, everything up to 255. You remember which one was the lowest, you keep that threshold, and you're done. That by itself will already be very fast. Very efficient, very fast. If you do some algebra, you can actually find out very simple algebra. Just plug in the formulas from the previous slide here, and you can find out that this, which is the total variance of the image, is basically the sum of the within class and the between class variance. Now, this is of course constant. It doesn't depend on the threshold. The image is just one image, and the variance of that image is constant. So we want to minimize this. This is constant. This is equivalent to maximizing this. Now, the probabilities and the means basically are very, very easy to update as we move the threshold in a very simple recursive formula, which is, add one more when we are moving the threshold. So basically, this can be computed very efficiently in a recursive fashion as we go from, let's say, t equals 10 to 11, 12, 13. We basically keep adding here, and then very fast we compute. We once again run from 0 to 255 on the t's. The difference is that computing this cannot be done explicitly in a recursive fashion, but this can be done explicitly in a recursive fashion where the t plus 1 depends on the t in a very simple formula. It's just, means and probabilities. Very simple. You keep adding and you get to the result. So very simple, either if you use the direct computation or if you use the recursive computation. You run through all the possible values of t, you pick the one that either minimizes this or maximizes this, and you're done. So before I show you some examples inside MATLAB, I want to tell you something. If you have a non-uniform background, like in this image, then Otsu is not going to help. Otsu's algorithm is not going to help, because you might have a binary distribution like we draw here, but then because of the bias of the background, this will not be a basic binary bimodal type of distribution. So I just explained you how to do Otsu's algorithm in the whole image. You can also do it in blocks of the image to try to get rid of the problem with basically a non-uniform background, and then you're going to get a different threshold for every single one of the region. Or if you want, you can actually do what's called a moving window. You can just do it here. Sorry, let me just get the pen. You do it here, then you do it in another window like this, and then you basically do it in another window like this. And then you can, for example, if you want, you can average the thresholds that you get in the overlapping windows, or you can create a function of the thresholds. So once again, as in many of the other algorithms that I have explained, there's the underlying concept, which is to separate the images to minimize that within variance that we just explained. Now, that concept you can implement in many different fashions, in the whole image, in blocks, overlapping blocks, non-overlapping blocks. There's a lot of art, and basically depending on the application what to apply. Once you do it, for example, as here, if you do it globally, let me just erase the annotation so it's easier. If you do Otsu in the whole image, this is what you're going to get. This is very dark. So it got confused with the letters in the distribution and in the optimization, and then it basically, the threshold, put it together with the letters, and the writing it's basically gone. Now, if you do it with a moving window, you get this beautiful result back. Once again, extremely, extremely simple. All what we are doing is to segment out the letters here. We are computing thresholds. We move a window, we just move regions, we move it, and we are computing thresholds with the formulas that I just explained to you. Now, let's see an application of this running inside MATLAB. In order to illustrate Otsu's method inside MATLAB, the first thing we have to do always is to load the image. So here we are loading the image. This is this operation. The next operation is what actually does the computation of the optimal threshold, the Otsu's algorithm that we just described. That's this operation in MATLAB that it gives us the level, gives us the value of the optimal threshold, and then we are basically gonna threshold the image following that value. So let's see the results of all these operations. We have them here, and let me just move the windows so we can observe them better. This is the image. This is the histogram. Now you're an expert in Otsu's method, so the moment you see this histogram, you say, wow, that's great. I can do a pretty decent job if I just compute that optimal threshold that should be around here, and that's a result of thresholding the image with that optimal threshold. It looks pretty nice. Remember, no special information. So for example, you might be able to see a few pixels here that were included as part of the background. Of course, without any type of smoothing, you will get rid and will get a very, very nice white object inside here. Here things are a bit different, and that's because, as you see, this part of the coin is relatively dark, almost as dark as the background, or basically as dark as the background, and that's why it was included as part of the background. Situation might have been different if we do Otsu's method in a local window or some other variant of Otsu's method, but the idea is very clear. For most of the image, which with a simple threshold, we get a very nice segmentation. And that threshold, we don't need to specify by hand. Otsu's method automatically computes for us. So let's go back to the slides and we finish this video. Thank you. In this video, we have seen another classical standard, very simple and very powerful image segmentation algorithm. Unfortunately, not all the images are easy enough for Otsu to segment or for the half transform to segment, and we're going to need more advanced techniques to be able to handle them. And that's going to be the topic of the future videos in this week. I'm looking forward to seeing you in them. I'm having a lot of fun, and I hope that you're having too. Thank you.